Recording is rolling, and it's Wednesday, November 12th. So picking up from Monday we got a new topic going on. This is momentum, which is a product of mass and velocity. This is a vector value, and it's conserved during collisions. Whenever you see collision, you should start thinking in terms of mass and velocity and adding up all the bits. Okay, so speaking of momentum being conserved, here's a general collision. Now, there's different kinds of collisions, but this poster applies to all collisions, which is that if you add up all the mass and velocities before the collision, here's like before the collision there got applied, and then after the collision, but morning, maybe they were down on each other, maybe add all the mass and velocity, it always equates. Hey guys, the fact that momentum is a vector, if something's moving to the right and moving to the left, could that be a positive and a negative value? Yeah, because what if you have positive 11 units to the right and negative 11 units here because it's going to the left? How much momentum would be in the system?
Zero.
Yeah, zero. Yeah, according to this vector value. Which means also, after they maybe pointing for down up to, would there also be a total of 0 units in the system? Yeah, okay, that's what conservation says. Okay. Now, of course, we did all these posters, a bunch of them. Okay, but one more that I want to point out is this one here. Impulse, which is a change momentum. So, like, what if you're looking at the open system consisting of only this baseball right here? It's getting hit by the bat. Now, that force from the bat is now an external force. Right? So, that's going to cause the baseball to change its velocity. Right? And maybe the mass stays the same, that's usually the case. Okay, so, that would be a change momentum for the baseball. And you get that by applying some force for some time. Okay, so it could be an average force for some time, or on a graph of force versus time is the area under the curve. Okay. Alright, so you guys good there? Alright, that's the main ones. Alright, so I got some demos for you guys. Some demos. Pull these up. Okay. And then we'll get to this page later. I want to show you guys how to set this up and solve these. But my plan is to have you guys work in teams. I want to do a lab with you guys. Well, maybe tomorrow. We'll see if we get there. If it takes out right. It involves these collision parts. And you guys remember AP? There's AP Classroom coming up due on Monday. All right, so let's do Galilean cannon. Well, this what you're about to see is a version of a Galilean cannon. Okay. Ooh, look at that! Yeah. Okay. So what we got here? We got a basketball. We got a tennis ball. No, suppose there was no basketball there. Guys, if she just drops the tennis ball, what's the highest the tennis ball could possibly rebound to?
From where she dropped it.
Yeah, from where she dropped it, right? And it couldn't go any higher than that, right? But we put the basketball underneath it. How, right? So when they all hit the floor, right, there's some momentum transfer, is a good way to think of it, right? From the basketball to the tennis ball, and the tennis ball go even higher than before. All right, got another one here, right? Same thing, maybe it's a golf ball, I think, maybe, right? So, yeah, it's the same premise. Pure, yeah, it's really fly up there. That's called Galilean cannon.
That.
What's up?
Guys, you should totally do that. I'm gonna do that.
All right, then, we got Magic School Bus Clip. So they're on this frictionless baseball field. Right, so get rid of all the friction. You just strip this down to the fundamental physics. Right, so we got these kids on this field. Oh, look, they're having trouble maintaining balance because, right, I mean, that would be true. You guys have gone ice skating. The first time you go ice skating, kind of hard to maintain balance because there's still a little friction to work. Right. Keep your center mass over your feet. Right. So she's gonna throw this ball in this clip. Oh, look at that. And she gets kicked backwards. Right? Now, what I'm interested in finding out is how fast is she headed back towards second base? You guys get that? How fast is she sliding back towards second base? Okay. Now, maybe there was sort of a convoluted way to find this in the past in this class. Like, well, if she applies some force to the baseball for some time, there's some acceleration, she gets the same force backward for the or something like that. But you can cut all through that if you know conservation momentum. So we're going to solve this one right here. And actually, I think it's this one of my posters. It's, they got it there at the end here. Oh, it's this one right here. This one right here. Okay. Now it changes to an icon called an ice skater and called maybe a snowball. Okay. But it's the same idea, isn't it? Okay. So guys, if they all start at rest on the mound, W smoothing, what's the total momentum in the system?
0.
Yeah, 0. Okay, so mass times velocity would be 0. There is mass, but no velocity. Okay, so here's my conservation equation. Sum of momentum before the throw equals sum of momentum after the throw. Okay, and guys, if you throw a ball or sometimes I'll bring up the example of a grenade explosion. Isn't this all just a collision in reverse? Like if you filmed this and ran to film in reverse, it would look exactly like a collision, wouldn't it? Okay, so there's zero momentum in the system. In the unit for momentum, well, maximum velocity, that would be kilogram meter per second, wouldn't it? Okay, there's no special name for that unit, it's just kilogram meter per second. Okay. So it all has to zero out. It's always zero because there's zero momentum in the system. This could be a closed system consisting of the person throwing the ball and the ball. Right, that's it. It's a closed system. Okay. So mass times velocity of the ball to the left matches mass times velocity of the skater in this case, or the pitcher going off to the right. Like I said. Okay. So all the momentum has to balance. Okay, so let's throw some numbers at this. Okay. So let's get this ball. I'll tell you the mass of the baseball is 0.145 kilograms. And let's say the speed of the pitch. We'll come with some number. Okay. Okay. And here's the pitcher going back the other way. Okay. And she has passed some mass. Here, I'll just make something up. Let's call her 40 kilograms. So what's her speed back toward second base? Okay, so we're solving for that. Now, speaking of this speed of throwing, what is this relative to? Is this relative to the pitcher or relative to a tree in the background?
Yes.
Yeah, let's go a tree in the background. So relative to something in the background. Let's say she's throwing this at 12 meters per second. Like that. So, okay. Because the fact that there's no friction on the ground, so she scoots back for second base. Okay. Do you guys see that if you do consider the difference in velocity between the baseball and her, it's actually going to be a little bit more than 12 meters per second? Maybe like 12 point something. Okay. So if she had been stuck into the ground, like if there had been friction, she was like dug into the ground and didn't move at all, but just like regular baseball. Do you think this baseball would have actually gone a little bit faster towards the plate? Yeah, great. But in fact, there's no friction, so she skated backwards. Well, maybe we get that number. Okay. Yeah, just keep in mind these things. So here's our framework. Now, sum of momentum before the pitch equals sum of momentum after the pitch. Forgot that. Okay. And guys, how much momentum is in the system again? Zero. Because everybody started out at rest on the mountain. 0 kilogram meter per second. Okay. Now that's going to go into mass of the ball times velocity of the ball to the left. Right. I'll throw these little vector arrows above. Right. Usually do that for this section. Plus mass of the pitcher, velocity of the pitcher off to the right. Okay. And I really want to know how fast does she head backwards second base. Right. So let's pop in some numbers. I got 0.145 kilograms here. You got 12 meters per second here. You got 40 kilograms here. Velocity of pitcher. Okay, so go ahead and solve that. I'll solve it off screen. You guys solve it. See if we get the same things. Alright, so somebody tell me how fast you headed back towards second base.
0.04.
You got what?
0.04. Negative 0.04.
Ah, all right. I got what Justin got. Okay. So this times this, then subtract it over, divide by this. Yeah, it would be a negative number. That's true. Yeah. So velocity pitcher is we got negative 0.0435. That would be meters per second because the kilograms cancels out. Get meters per second. Describe the velocity. Yeah, that's not fast. All right, pretty good. You guys good there? Very good. Alright, the momentum is conserved. If you film this and ran the film in reverse, it would look just like a collision. Actually, a special kind of collision. So we talked about different categories of collisions. Actually, this is probably a good opportunity to review some posters anyway. Okay, so we've got momentum, velocity. with closed systems, momentum is conserved. Actually, we just did one of these. Right? When we get to maybe a ball bit hit by a bat, we'll consider just the ball. Maybe it's an open system, it can be an external force and momentum change. Right. So momentum is conserved. Looks like this. You guys should solve this one. You guys should solve for. And then we got to different kinds of collisions. So here I got two different kind of balls here. This orange one, very bouncy. This black one, not so bouncy. Right. Now, yeah, so if something's perfectly bouncy like this, you would call this what kind of collision?
Wow.
Elastic. Yeah, elastic. And what's the physical property that's special about this? Not only is momentum conserved, but what else?
Kinetic.
Also kinetic energy in the system. If you add all the kinetic energy that's before and after, it's all conserved. Now, again, this is not universally true. This is only true for this very special kind of collision where it's really bouncy. Another example that he uses Newton's cradle. Okay, this is pretty much elastic right here. Okay, that's a very special kind of collision. Okay, but what about this collision? Is kinetic energy conserved there?
No.
Definitely not. In fact, if you add the kinetic energy post collision, it will always decrease. Okay. But is momentum conserved? Yeah. So here I'm showing like two things colliding. Right? These are all in one dimension. So if you add up all the mass velocity that's before and after, they do equate. Right? But look at that, it makes one giant mass because they stuck together with one common final velocity. So that's called perfectly inelastic. Okay, so there's a little bit of review. Okay. All right. So let's look at. Of course, got a bunch more, but. For sure. All right, let's look at this page. All right, so I gave you guys a big at the top. Let's get that real fast. We have general conservation momentum here. Here's perfectly inelastic here where they stick together. Okay. Here's perfectly elastic. Well, this is the end result. I would not expect you to memorize this, and neither does AP. I mean, if you give more space in your mind to memorize this, so you do, then that won't hurt you. It can help you. Okay. But this is the result of a system of equations, and it's kind of hard to find this equation in textbooks or on the internet. So if you hold on to your notes from high school, then when you go to college and they ask you perfectly elastic, you won't have to solve a whole system of equations from scratch. Like momentum conserved, kinetic energy conserved. It's a lot of paper and a lot of time. Okay, so this is always the end result. Impulse, mass exchange velocity results from force times time interval. And then if you want to quantify how bouncy is a collision, like on a spectrum from perfectly inelastic to perfectly elastic, right? Because realistically most collisions are somewhere in the middle. Right? So you can quantify that with coefficient restitution, which is something, again, that AP does not ask, but it's good to know, really. That's number one. Two objects collide and bounce off each other, so that the total kinetic energy is conserved. For example, on Newton's cradle, this type of collision is known as what? Elastic. Number two objects collide and stick together so that some of the kinetic energy is converted to other types of energy, like permanent deformation or heat loss or something. This type of collision is known as inelastic. Right, so you guys got some categories of collisions. Okay, number three, we got a general collision here. Two objects with measured masses. I got mass A and mass B. You guys got it, mass A and mass B? Okay. Now, you guys know there's like 10 different versions of this paper, so all of us have different numbers. That's normal. Okay. But we all have the same premise question. So we've got two masses here, mass A and mass B. They collide head on, so just a single dimension, maybe along the x-axis, resulting in these given measurements. So I have pre-collision velocities for each of the objects, so we know how fast they're headed toward each other. And post-collision, I did get the rebound velocity of one of the objects, but not the other one.
Oh, we gotta find the other one.
But can you solve the other one? Yeah. Okay. So here, I'll do at least one of these out on paper with you guys. Okay, so I think number three is a good opportunity here. So I'll say sum of momentum before the collision equals sum of momentum after the collision. Okay. So that's the framework. Then mass A, velocity A before, plus mass B, velocity B before, okay, before the collision, okay, equals, right? And everything after the collision. Mass A, velocity A final, plus mass B, velocity B final. Okay. And we should know all the numbers except for that one right there. So if you know everything except one value, you can solve for that, right?
Yeah.
And so I'm going to plug in the numbers from my page, which are probably different than yours. So I got 1 kilogram here, which also shows up over here. Mass B on my page is 2 kilograms. Twice massive. Then before the collision, I have object A coming in at 3 meters per second. And object B coming in at, negative 3 meters per second. Okay. Now, in this case, a positive versus a negative velocity, doesn't that just mean they're coming in opposite directions? Is that what I mean? Opposite directions? Okay. So, guys, what if both numbers were positive? Could you have maybe like a fender bender, like a fast car bumps into a slow moving car in front of it? Right. In that case, maybe they both have positive velocities, just different value. Right. And then after collision, I did tell you one post collision velocity, and on my paper, this is listed as -1 meter per second. Okay. Then we can solve for BB final. Okay. Now, before we go plug in and check on the algebra, let's look at big picture here. So it looks like these two objects were headed sort of towards each other because they got opposite signs on their velocities. Okay. And then if I just focus on object A in this case, see how, hey, does my object A reverse direction? It doesn't rebound because it was going to the right. Now it ends up going to the left after the collision. So it's something kind of this, like boing, or something like that. Huh. So solve here. Got it. 3, 6. The total momentum in my system, just throw in the middle step. It's like this many kilogram meter per second.
Yeah.
And sum this routes into object A and whatever's left for object B. Okay. So +1, +1. That's -2 equals BB final. Like this. Okay. So as an answer on my paper, yeah, I just said as an answer choice on my paper. Okay. Are you guys also getting an answer choice on your paper for your numbers? Yeah, you guys are. Okay. Now, you know what? Here, I just picked a paper randomly, so this probably didn't work out for everybody. I mean, what I'm about to say. Guys, my collision, now that I'm looking at it, actually is a special case. What kind of collision is my collision? Perfectly what? Inelastic? How'd you know? Because they have the same final velocity. Look at that. Did my two objects stick together? Right. No, that may not have happened on your page, but it did on mine. So this is what happens on mine. No, move together. So this side. Here, I'll do that again. That's pretty much what mine is saying. I want to do another question related to this, though. The scenario is: what if I add up all the kinetic energy before and after? Because what has to happen to kinetic energy? Definitely anytime they stick together. It will always decrease. So if I do sum of kinetic energy before and sum of kinetic energy after, I will just do this on my calculator screen. Isn't it something to do with 1/2 mv squared? So 1/2 times this mass times this speed squared. And remember, kinetic energy is a scalar, so you can drop all the negatives and just everything can be positive. That's fine. Okay? Plus 1/2 times this mass times this speed being squared. It looks like before I had 13.5. What's the unit for energy? Energy. Joules. Okay, so before I had 13.5 joules. Okay, so do you guys think that after the collision, I have to have less than that? Better. Okay. So 1/2. Here, I'll just make one giant math of 3 kilograms because they are effectively. Okay, times 1 meter per second being squared. Okay. Yeah, it's only 1.5 joules. See, it went way down. Okay. So before I had a bunch of kinetic energy. Post collision there was less.
Adding through number collision on the
Get that? All right. Okay. Number 2. Two objects collide head-on, resulting in these measurements. It's very similar, except that now you have a bunch of post collision data, and I want to know before the collision what was one of the unknown velocities, which is really just the same thing as this. Isn't that really just what we did? except now you're solving for a before case. Okay. Was like through your book. One of your book questions had something to do with a car collision. It says you're some kind of forensic investigator. You want to figure out how far fast was one of the cars traveling leading up to the collision. Maybe you have enough information, you look at skid marks on the road to figure out everything else. Okay, so you're solving for a before collision case, but algebraically, it's no more complicated than what we just did because you have everything except for that value. You guys got that? Okay. Now, I do want to give you guys some independence and agency to try this out and work with each other. So I just want to show you guys how to set up most of the rest of these pretty much. Number 5, 2 objects collide and stick together in a perfectly inelastic collision. Given the masses and initial velocities, find the final velocity. Oh, you guys know that just the table is one column short of everything we've been doing so far? Because when they stick together, they'll have the same final velocity. Yeah.
That's true.
Could you guys apply this perfectly inelastic right here?
Yes.
And of course, you guys know you have the thumbnail notes. I gave you guys these the very first day of school, but also the posters are hanging up over on that wall. All the blue banners. You guys are seeing, you have access to all these. Okay, number 6. This one. I always get questions about this one every year. So I'll help you guys out with this one a little bit. You got a grenade flying through the air at some given velocity, explodes into 2 parts, which travel along the same direction that the grenade was originally traveling. So we're still thinking it's sort of linear. At what velocity is the set? So it breaks into 2 pieces. I told you the final velocity of one of the pieces, but what about the other piece? And then I told you pretty much exactly how to do it in the parentheses here. Apply the perfectly inelastic collision formula in reverse. Because isn't it true that if 2 objects collide and stick together, so like this, and then you run that film in reverse, it would look just like an explosion, wouldn't it? You see that? Just like an explosion? Okay. So really, just this right side turns to the left side. Okay. So what's initial is that it was one giant grenade, just one giant mass. So you change this B final to B initial. And then post explosion, it breaks into 2 separate pieces. So this is final, this is final. You guys got that? You guys figured that out? Okay. So all you do for an explosion is just take perfectly inelastic, you just change initial and final. Okay? It started off as all one mass. This is initial. It ended up as separate masses. These are final. Okay? Can you guys see that? Not kind of put that over. Okay. So that's not bad, right? How about this? Guys, what if you ran a kinetic energy check? Oh, I know I did before for what looked like an inelastic collision and the kinetic energy decrease. But what about for the grenade? Guys, what do you think happens to the overall energy in the system after it explodes? Would you get more or less energy in the system?
When you get more, it explodes out.
Yeah, guys, that chemical energy and maybe the gunpowder or whatever explodes it, pow, that now manifests as mechanical energy. So the mechanical energy in the system had to increase. Right. So here's another way to look at it. When they're stuck together, maybe there's overall less mechanical energy, and when they're exploded into 2 different parts, there's more mechanical energy. So it's consistent. If you run the film in reverse or whatnot, it's the same idea. Actually, I do have a poster just for a grenade, so may as well show that to you guys too. See this one right here. So while I got this one out, remind you guys what the purpose was of putting this together. See what says the center mass of the grenade is unaffected by the explosion. Okay. So especially throw a grenade and it doesn't explode off, it's a dud. And it lands right here. So it's a dud. It just lands with one solid piece right here. That's okay, right? Okay. Nice parabola, whatever. Projectile. Okay. Now let's go back up. What if this grenade explodes into 1,000,000 parts? 1,000,000 parts. If you found the center mass of all those parts, guess where that center mass would land? Right where the original dud landed. Yeah. Right. What about this? Here's a question I've seen AP ask, I think multiple times in the past. What if the grenade explodes into 2 parts? And to kind of simplify it, let's say they're equal sizes, so equal masses. Okay. And the grenade itself would have landed like 100 meters downrange, but now one of the halves lands 200 meters downrange. Guess where the other half lands? Yeah, back where the guy was originally throwing it, because the center mass would still average to where the dead would have landed. Yeah, it's it. Yeah. Right, so look for that question. It's a good chance to be asked that on the AP exam. Okay. That next to number 7. Oh, number 7. I like this one. Is 2 objects given masses collide head on perfectly elastically. We haven't done one of these yet. Perfectly elastically. What therefore is the final velocity of object A? So I'm just focused on a single object, but give you guys some ways to think about this, right? And we'll maybe throw some other questions at you guys. Okay? So momentum's conserved, although that's true for any kind of collision. But what's special to elastic is this condition right here. Kinetic energy is also conserved. Okay? Now, I told you guys on Monday, and I'll tell you guys again. AP rarely asks about elastic collision, but not never. And the two ways I've seen AP ask or like incorporate elastic is one, it could be a small part of a larger question. So they say, what if you have two equal masses, one starts at rest and one is like roll off a ledge and pow. Okay, well, okay, it's trying to stop some time. But see, what's going to happen is that they will exactly reverse they'll exchange velocities and all other properties. So pow, see how one came to a dead stop? Okay. Now it's only true if they're the same mass as each other and it's perfectly elastic. Momentum's conserved, but kinetic energy is also conserved, and that's the outcome. Okay. The other way,
I'm like,
okay, well,
what is
I'll
that?
table that later. Okay. The other way that I've seen AP ask perfectly elastic is they'll give you a multiple choice set of options. They'll say which of these represent perfectly elastic, and the fast way to solve it is to go through, starting with A and then B and then C and so on all the way down until you can confirm that both of these green conditions are validated, right? Especially this kinetic energy condition. Right? Or if you memorize this gold box, then that'll get it for you too. So on number 7, this page, here, since I have it solved for you guys ahead of time, it's just a gold box. You could on number 7 just do this. You could say, well, velocity A post collision is, and it's always the stride fraction. Again, guys, this gold box, make sure you guys know what you're looking at, is the result of the system of equations of these two green equations. Okay? It's always this gold box. Velocity A initial difference in masses plus 2 mass B velocity B initial all divided by sum of masses. Okay, so that's always for again like perfectly balanced, perfectly elastic like that. Okay. Now here's another question though: is this is only focused on object A? Right? Like if it gives you guys sort of a picture, if we got a mass A and a mass B, right, headed toward each other, maybe like this, that pow, right, bounce off each other. They're gonna bounce off each other, right? And then this equation tells you mass A post collision. Right? Can you guys think of a way to figure out what's happening with mass B post collision?
No.
How can you do that? Yeah, I like that method. Did you guys hear Justin? Guys, could you just change the definition of what's A and what's B? Could you just swap all these subscripts? Say velocity B final is just keep go B A B A. Just swap all the subscripts. Right, just change the definition of what you're focused on. You can do that. Okay. And then another way to do it too is once you solve final velocity of object A, could you just go back to general conservation momentum and solve for the now one unknown velocity? You do that too, right? So there's a couple of ways to do that right there. You can do that. Right. Then number 8, number 9, both involve coefficient of restitution. Let's say like how bouncy is an object. I do want to do a lab with you guys that looks a lot like number 9, probably next week. But how bouncy is a collision? So here, this one is pointed out. Right, so whoops. Let's start. Hold on. I got another one.
I just remembered how to solve the coefficient of restitution without using
Where did it go? Here it is. Okay. So this great textbook way to get coefficient of restitution is you look at the difference of velocities before, which is now this denominator, the difference of velocities after, which is this numerator. Okay. Guys, delta in this context means difference in. Okay, not changing, but difference in. Okay, difference velocities. Okay. Guys, also remember these are vector values. Velocities are vectors. So here, see if you guys follow. You guys suppose this is 7 meters per second to the right, and this is 3 meters per second to the left. what's the difference between 7 to the right and 3 to the left? And don't say 4. 10. Because isn't 7 minus -3 equal to 10? Right? So that could fit in right here in this numerator, something like that. Okay. Also, you can take the absolute value to make this number always positive, or do you guys notice how I swapped the subscripts, got a minus a on top, but a minus b on the bottom? Okay. To make it always just a positive number. Okay. And how many of you guys remember for Monday? Guys, this value is always bounded between what and what?
0 and 1.
0 and 1. Yeah, because if they stick together, what's their difference of velocities post collision? That would be 0. So the whole thing would be 0. Okay. But if they collide perfectly elastically, like Newton's cradle, boing, then this fraction always comes out to be 1. Okay. And realistically, you get something kind of in the middle. Okay. Next question, number 9, is a specific version of this, where the two objects colliding might be a ball and the entire Earth. And maybe you have a tiled floor because the surface is also matter. Okay, so if the Earth basically isn't moving, then wouldn't the difference in velocities just be represented by the velocity of the ball? Because the velocity of the Earth, we're just going to call it 0. You can say, well, what's the crash speed? What's the rebound speed? And then take the ratio, rebound compared to crash speed. Which, if you go back to a few weeks ago, conservation of energy, does this look familiar right here? The crash speed is square root 2gh. And you can also say rebound speed is root 2gh based on the rebound, right? Okay, the 2g cancels. Okay, so just a reminder what you guys saw on Monday, but we saw all those. And the last couple of questions here are impulse questions. Impulse. So that's this one right here, impulse. So mass times change of velocity results from force times time interval. So I'm looking at maybe an open system consisting of only the baseball, maybe. Right. And on number 10, I'm looking for the change of velocity, and number 11, I'm looking for the average force, but I gave you everything else. Okay. Guys, out of these 1, 2, 3, 4 variables, if you had 3, could you just solve for the 4th? Okay. Now, if you want to do one of these with you guys, I'm going to do number 10 with you guys. So let's do that. All right. So I got the mass of the ball is 0.15 kilogram. We're solving for change in velocity. I told you the force was 190 newtons. No, this would be an average force. Let's just go that way. Let's say the time interval of contact with the bat is 0.03 seconds. Okay. So I got mass times change in velocity results from force, like an average force for some time interval. I'm solving for this delta V. So let's put in 0.15 kilograms for the baseball. Delta V we're solving for.
This is honors.
Got 190 Newton force right there, and 0.03 seconds right there. Right, like that. Right, so 190 times 0.03 over 0.15. So I'm getting the delta V, the change of velocity, is 38 meters per second. Okay, now that's not too bad, right? Okay, that's okay for number 10. Okay. Right. But one of the reasons I want to do this with you guys is to see if you guys can follow the full story of what's actually going on. So here, I'll draw a picture over here in this margin. Suppose the pitcher throws the ball towards the plate at, let's say V pitch is like 20 meters per second. You guys got that? Okay. And then here's the bat. And then pow! The bat hits the ball and sends it the other way. How fast? V final. Let's say to the right equals what? And let's say all these numbers apply. So this is what's going on. I'm trying to draw a picture. So my pitcher threw the ball towards the plate at 20 meters per second. Bat hit ball. Pow! How fast the other way?
Wait, what?
I want somebody to tell me how fast this ball is headed back towards the outfield.
18 meters.
Huh?
18?
18? Yeah. 18 meters per second. There you go. Okay. Because, guys, delta V. Yeah, keep in mind there was a direction change. Going to be 18 meters per second minus negative 20 meters per second. There's a sneaky hidden negative right here, isn't there? It's going, there's a sign change. That is the same thing as 38 meters per second, which aligns with that right there. Same thing. Okay, you guys get? All right. And then if you guys saw a force versus time graph, if you're going to see a bunch of force versus time graphs, you guys know you could just find the area under the curve, and that could also take the place of the symbols right here. Okay, you guys get that too? Yeah. Okay, we have about 12 minutes. Okay, that's not too bad. So I'm gonna give you guys some time to work on this either by yourselves or with each other, and I can walk around and help you guys out.
No idea.